All right, and this lecture is just going to be a quick review, hopefully, of communities and how communities are organized, and some fire effects on how communities are going to be assembled after the fire, or and of course it's going to depend a lot on what survives the fire and what comes back, obviously. Just a couple of quick definitions: populations of species that coexist in space and time and interact directly or interact indirectly. Note the difference between community and ecosystem there in terms of that. Basically, community, we're talking just mainly the biotic components of an ecosystem and not the physical environment. And also, typically, when ecologists talk communities, we're really not thinking about how humans fit into the mix. Uh, I think more and more, however, we really need to think about humans as members of communities, and obviously with a lot of the work in sustainable ecosystems and ideas of resilience and so on, that's becoming more and more the case. I'm sure you've all seen these trophic levels. I'm not going to go through this at all, but just keep in mind that obviously when we're dealing with communities, we're dealing with multiple different trophic levels in terms of plants as primary producers, etc. And then don't forget that there is again this whole detritivore as well, decomposer side of the trophic cascades and energy, both energy and matter within a particular community. And of course, all of these, this is again, they're dealing with the members of plant and animal communities, biotic side of things, all of this with operating within the context of the physical environment, the abiotic components. Just a couple of concepts, and again, I'm sure most of you have probably heard of these fundamental niche, the idea of where a particular organism can grow again, particularly thinking about mean annual temperature, mean annual precipitation. Um, And then the realized niche. Now, again, this is within the context of the community itself, because where in this case it's thinking mainly about competitive exclusion, so that another species is going to be a much more successful competitor or user of those resources, and be able to keep that other species out of that particular location. Um, However, there's also, of course, fire may limit the species' ability to establish and persist because of either, too much, too little, differences in fire behavior. Even though, say, if you're looking at, for example, mean annual precipitation and mean annual temperature, that those two factors alone could, that the species could grow and thrive at that particular location. Again, coming back to Bond et al. And some of the other papers we've read earlier in the semester. So in this case, again, sort of these are just the basic sort of Venn diagrams of these things where you have two environmental, and these are just, bivariate displays of the environmental uh, conditions that a species needs to persist. In this case, you have E1, E2, again, thinking about perhaps mean annual temperature, mean annual precipitation. So the pluses are where the species can persist and the zeros are where it can't. It needs that particular combination of those particular environmental variables. Well, on the right-hand side then is the realized niche, because then there's places even within the fundamental niche that the species cannot persist because of, for example, a more successful competitor, or, for example, because the fire frequency is too high that that plant can't get established. Again, Bond et al. Certainly a few, what affects plant community composition after fire. All of these, I mean, you've probably gone through these in terms of, what persists, what is able to survive by propagules that are on site. Certainly, how do seeds get back into the site in terms of dispersal limitations or dispersal ability. Um, the post-fire climate and environment, obviously. I mean, if it's going to be too warm or dry, this has obviously led to a great deal of, particularly next week, our next lecture is going to be talking about successional ideas. And certainly climate is an overlooked component in many cases because it can be too warm or dry for particular species to establish in a location. What kind of herbivory competition may begin biotic interactions, obviously, that in the fire. For example, I mean, again, shade tolerance is a big one. Was the overstory, if it's in a forested ecosystem, was the overstory completely removed, or is there still surviving overstory individuals? In which case, the shade intolerant species may not be able to establish. And of course, again, as we've talked about several times, erosion and soil damage. What sort of nutrient dynamics do we have? What sort of soil biota is still present or not in the stand, in the site? So particularly thinking about the post-fire environment, people have used clear cuts as an analog for at least extensive crown fires. Obviously, if there's still an overstory left, it's not going to be a clear cut. But just to go through, how that changes, and next lecture is going to be talking about successional dynamics. Obviously, certainly the environment is going to completely change, not completely, but huge changes are going to occur if you lose the overstory of a forested ecosystem. So this one, just go through a few of these as an example of what could happen after a crown fire, and using it as, this was a study that was done in just looking at a transect between clear cuts and into the forest, and some of the changes that occurred. So different plots with distance from the clear cut and back into the forest. So first of all, obviously very big differences in temperature ranges. So these are the diurnal temperature ranges, high minus lows at the forest floor surface for the different seasons. And obviously you can see that the diurnal change at the both in the clear cut and slightly at the edge, there's certainly an edge effect as well into the forest. Was pretty great. This diurnal temperature range then will very much limit what kind of propagules can get established, what's going to be able to get established in the new site. And it's because, of course, that you don't have any trees providing any long wave radiation back to the surface, no shading, so greater heating in the day and greater cooling at night. Of course, there's greater snow accumulation. So here's snow volume on the y-axis in this one in distance. And again, it's just because you've lost the overstory, obviously, that there's a much greater snow accumulation. There's been a lot of work on the hydrology of clear cuts and harvest in general, on particularly increasing snowpack and providing more water, particularly in, for example, Western North America, more water to watersheds. So you can get rid of the trees, and you can certainly increase the amount of water that's flowing down to human habitations and dams and rivers and such. Just a side note here in terms of interception, capture of precipitation by trees and plants in general. But if you have more caught in the canopy, obviously you get a lot more evaporation if it's rain, or sublimation in the case of snow. So directly from solid to gas as sublimation. Through fall, the amount of precip that passes through canopy, you've probably seen these canopy drip and so on. But again, if you still have that overstory left, or any part of the overstory, certainly the hydrology of the stand is going to be completely different than if it's completely removed. Litter fall inputs, obviously, you don't have any trees, so certainly less litter fall. And then because of this diurnal swing in the temperature, that decomposition is going to be faster in the clear cut. You get more snow accumulation, more water accumulation, more higher temperature changes. So the decomposition of any type of litter, again, in terms of nutrient dynamics, is that after the fire is going to be completely different. Now, one thing too to really point out that the obviously a clear cut is not a true analog for a severe crown fire, simply because you do have a lot of still woody biomass left, or fine needle biomass, fine wood biomass left after the fire that would potentially be removed, obviously, in a clear cut. So these are not complete analogs, but certainly gives you the idea of just how big of the changes could occur after a crown fire. Again, major changes in terms of nutrient losses. I mean, I mentioned this before. So in this case, here's nitrogen on the x-axis, or on the y-axis, excuse me, versus fuel consumed. And you can see in surface fires, there's, typically not a lot versus a crown fire. So it does depend, but a pretty good linear relationship, obviously, between how much nitrogen is lost, mostly volatilized. It goes up in smoke. Some of that nitrogen, of course, still stays around in terms of char and on the fuel. Now, in terms of replacing this loss, some comes in precipitation. A lot comes in fixation by nitrogen fixing, mycorrhizae and other, processes within the soil, and then certainly fertilization in some areas as well, but not in natural ecosystems, but precipitation or nitrogen fixation being the two biggest ones. One interesting, there is this, again, successional dynamics, and in many places we do have nitrogen fixing shrubs. Ceanothus in the western North America is a big one. Other leguminaceae plants come in. They come in either from sprouting or from buried seed sources, seed banks. But again, prolonged fire free periods can exhaust soil seed banks. I think I've mentioned that before as well. Nutrients are lost, obviously. I mentioned this before, so it depends upon certainly the erosional environment, how big rain, how often and intense rainstorms might be after a fire, but certainly a lot of ash can either be blown off or washed off of a fire footprint, and all of those nutrients are gone and will need to be replaced through time. So again, very, very changed environments post-fire in many cases, and it depends, again, largely on how much is consumed, if it's just the surface fuels versus the surface and ladder fuels and canopy fuels. Just the last couple of slides here is just to mention this. I've mentioned this before, but the burned area emergency rehabilitation. The United States federal agencies will have this bear response team, and it's immediate stabilization right after fires, typically in a lot of the fire footprints. This is a map of the Hayman fire, the bear burn severity that was mapped from satellite imagery, and we'll talk a lot more about Hayman in a couple of few weeks. But different, a lot of this is just to basically control erosion. Needle cover is very important, but damming on slopes, either by just, in some cases, felling logs across slopes, not so much digging out channels and so on for them, but as long as there's a barrier to slope to soil movement down the hill, and of course nutrient movement as well. In channels, obviously, there's a lot of work that goes on. Again, a lot of these bear treatments, in some cases, for example, after Hayman, there were several $1 million that were spent on. All of these were from Hayman. These photographs are from Hayman. Aerial mulching. In this case, a hydro mulch that also has not only seed but fertilizer in it as well. Aerial seeding. There's been a number of studies on aerial seeding and how much it helps, so on. In most cases, there's enough of a soil seed bank, even in these high severity areas, that recovery, even without any type of artificial seeding, natural seeding will come back in. So in some cases, there's been a lot of controversy about how much seeding. There can be invasive species. At Hayman, there was a horror story about in some of the straw bale mulching that they did, the aerial mulching, there was actually cheatgrass in the straw, and cheatgrass seeds. So all of a sudden there was areas that never had cheatgrass before that did have cheatgrass after the seeding. So it can be a problem more than a help sometimes. Thanks.